Okay, hello everyone. Today I'll be presenting on resonance and filters, which are two fundamental concepts in acoustics and speech science. We'll explore how resonance shapes sounds and how filters modify it. So starting off, what is like a resonant frequency? So that is the frequency at which an object vibrates with maximum energy. So it's pretty much like the most prominent frequency with least amount of opposition. And this resonant frequency has certain properties as well. So we're looking at objects with mass and inertia. So the larger the mass, the longer it takes to push an object. And we're talking about inertia. We're talking about properties that resist change in motion. So pretty much, if an object's already moving, it does not want to stop moving. It's resisting that change, and vice versa. If an object is still, it's not moving, it does not want to start moving. It's going to resist that change. And there's also a delayed initiation that continues past rest position, which means that um, it makes the object continue vibrating even after the force stops. So when we're talking about larger mass, we also mean that there's greater inertia, which means it's going to take more time to accelerate, but also more time to stop. There's going to be longer vibratory cycles and a lower frequency, and vice versa as well. So we have a lower mass, we're going to have smaller or less inertia. There's going to be less time to accelerate, less time to stop, shorter vibratory cycles, and higher frequency. So here I have an example of the concrete and the styrofoam. So concrete has more inertia. So it wants to resist that change in motion. However, once you're able to move it, it takes longer for it to stop. It has more resistance to air and it will technically vibrate longer. While the styrofoam, you think about it, if you even just flick it or barely move it, it will move quickly. However, it will stop almost immediately after the source or the person who moves it is removed. So also for resonance, we have to mention elasticity and how it's measured stiffness. So when we're talking about elasticity, we're talking about how well an object returns to its original shape after being deformed. And with stiffness, talking about the amount of force needed to move or stretch an object, or in this case, also to displace it to a certain distance. So stiffer objects require more force to be displaced because they resist motion. And when a stiff object like a spring is stretched, it stores more recoil force, causing it to snap back faster once the force is released. And this causes it to move quickly, so it completes each vibration in less time, meaning that it has a higher frequency when vibrating. So we can think of this of like vocal folds. So when vocal folds are tense or stiff, they are producing higher pitch. So and especially when they're like lower or yes, more loose or even swollen, they vibrate slower, lower pitch, so they sound more low like this. Well, if we're tensing them, yeah, so it's pretty much a higher pitch. So pretty much here are the formulas that we could use for resonant frequency. So when we're talking about resonance, we're also talking about like the quality of voice, or what makes one voice distinct from another. And we're gonna mention pretty much how that works as well. Okay, so when we're talking about the vocal tract configuration, it pretty much acts like a tube that shapes sound waves coming from the vocal folds. So the shape of the tube is influenced by the articulators. So the articulators include like the mouth, the mandible, lips, teeth, and so on. And these movements change the cross-sectional area of the tract from the glottis all the way to the lips, influencing how frequencies will resonate. And here we also have a picture of the area of function, which is a graph that shows the diameter or area of the vocal tract. So when talking about acoustic resonators, so tube resonators, like the vocal tract, can support multiple resonance, which means that it can vibrate at different frequencies at once. And we also have to talk about the cross-sectional area, kind of like we mentioned right now. And this is like the area that affects wavelengths and frequencies that can resonate. So when talking about cross-sectional, we have narrow and wider areas. So narrow areas are shorter wavelengths with higher frequencies, and wider areas are longer wavelengths with lower frequencies. And we can also mention the different types of tubes that we have. So we have tubes that are open at both ends, closed at one end, and constricted at different locations. So we're talking about a tube that's open at both ends or closed at both ends, which can also be the case. We're talking about tubes that pretty much are, so for this example in the graph, we have sound that's being emitted to the tube, and we have multiple frequencies, which will cause also for multiple wavelengths technically. So we have ones that's pretty much twice the size of the tube, one that's exactly the size of the tube, and one that fits, it's pretty much half of the tube as well. But for tubes that are open or closed at both ends, we want to apply the half wavelength rule, which means that we have to double the length of the tube to know the wavelength. So, and this is to find the resonant frequency, or pretty much the frequency that's most characteristic to that tube. So here, let's say if we wanted to do some math, let's say for this example, if we're trying to find the wavelength of this tube, it starts with 17 centimeters, but since it's at half, so we have to multiply that by 2, which gives us the 34 centimeters. And then we have, for wavelength, we have wavelength equals speed of sound. So speed, we'll just be S over frequency. So this rule will be technically cross multiply. And then as well for speed of sound, it will be easier instead of just using 340 meters if we use 34,000 centimeters. So if you pretty much multiply 340 times 100, that gives you 34,000. We have centimeters over seconds divided by frequency or by wavelength, which is 34 centimeters. And we'll get a total of 1,000 hertz, which is our F sub R. And then if we're doing a tube resonator that's closed at or open at one end, we're going to use the quarter wavelength rule. So maybe for this past example that we looked at, so we did 17 centimeters. In the past example, we did times 2 because it was half. However, right now, since it's a quarter, we're going to multiply by 4, which will give us 68 centimeters. And then we apply the same thing as last time. So we'll, to find frequency, we already have wavelength, so we can just cross multiply and instead do 34,000 centimeters per second divided by 68 centimeters equals, and I'm pretty sure that's 500 hertz. Let's just confirm real quick. Yes, 500 hertz. Okay, now for our first example. So if if I have a tube that's open at one end, I should use the quarter wavelength rule. Is that true or false? And that is true. Correct. Because remember, if it can be open at one end or closed at one end, that will be a quarter wavelength. But if it's open or closed at both ends, we'll use the half wavelength rule. We can see here, open at both ends or open or closed at one end. So now let's, instead, if we were maybe trying to find the speed of sound. So what would you do in that case? So in that case, it's just easy because we just have to multiply. So let's say for that example, we have 17 centimeters. And then that use, if we can see the centimeters is times 2. So they use, that means it's a tube that's open or closed at both ends. So times 2 equals 34 centimeters. and then we're going to multiply that by the resonant frequency, which is 900 and 998 hertz. And that's going to give us 34 times 998. The speed of sound used for this picture is 33,932 centimeters over second, or we can also divide this by 100 and then it will be 339.32. Okay, so kind of like I mentioned right now, the the vocal track and the source is affected by the different the shape of the vocal tract, and that is affected by the different articulators that we have, so like the mandible, the lips, and the tongue. Here you can see in this picture how switching the shape of the articulators in the vocal tract can create different sounds. And when we're talking about transfer function, we're pretty much mentioning how there's an input to something that we put into a system. That system usually filters it and then comes out with something different, so the output. So here we have the analogy or the metaphor of the bread. So if you put a bread, that will be your input you put into your system, which will be a toaster, and then um, the output would be a burnt piece of bread. So we're talking about shaping sound and source, kind of like how we mentioned right now. So the acoustic resonators or the articulators are what helps modify the output. So we do get that input from our vocal folds and the production of sound. And then the articulators and the vocal tract are what shapes it, gives it that specific voice that we each have, and then comes out with a different output. So when we're talking also about transfer function, we have here the pretty much how an input is put once again into a filter and then comes out with different output. This is where we can mention or see the difference between fundamental frequency or f sub 0 and um, resonant frequency or f sub r. When we looked at in the past module of fundamental frequency, pretty much stated how or hypothetically F sub R or harmonic one was strongest throughout the whole system. So technically H1 would have been this one. However, for now for resonant frequency, we're looking at the strongest frequency component at output that goes through a system. So here, like technically H1 or harmonic one or F sub 0 is not the strongest one. If we see here, it's actually one, two, three, the fourth one. Here we have pretty much a more example of that filtering and how it affects it. So once again, we have the input is put into a filter and then the output comes out with yeah, a difference. Okay, so when we're talking about factors that affect resonance, we are mentioning pretty much how energy is lost because when a sound is actually projected forward, so this is it loses amplitude throughout the time because of factors such as like friction, absorption, radiation, and gravity. And where we're talking about types of filters, so these are pretty much filters that affect which type of frequencies are allowed. So when we're talking about low pass filter, it means that it allows for the lower frequencies to pass, canceling the high frequencies. High pass filters allow the higher frequencies to pass and cancel the low ones. The band pass cancels like a few of both types of frequencies or allowing a specific range. And then the band reject blocks a specific range. It's usually that middle part. And this is important because it can help calibrate which system to use for a hearing aid. So maybe someone might need help with through a hearing aid that they need to, so they can hear the lower frequency. So that's something that they will do to calibrate an audiology. And this can also be done for high pass, and band reject as well. So when we're talking about types of filters, it is important that we also mention kind of like the cutoffs that we have for each one. So we go back to the next page. So we have these five principles of parameters of filter. So there's the center frequency, the upper cutoff or f sub u, the lower cutoff frequency, fc, bandwidth, and the rejection rate or attenuation rate. So you cannot really see it here, but technically for this low pass, this is the cutoff frequency. So that means that there's a f of u. So that means a upper frequency cutoff. And in this cutoff, we would usually see that little curve that would mean that there's like a negative 3 dB from the FC. And here we also have the high pass as well. So we can see we have an F sub L here at 2000, and then there's a 10 dB per octave loss. So if we go to the next octave, which will be 1000, this is 10, then 500, 20, and so on. Bandpass pretty much accepts the kind of middle ones. So here in bandpass, what we want is actually all of this, what's in the middle. And band reject would actually not want everything that's in the middle. So it's kind of like exactly the vice versa of band reject. And kind of like an example that I have for me that's been helping, to be honest, or kind of I thought about was is kind of like if you were going to a party, a club, and there was a bouncer. This bound, you know how in certain clubs there's like a ladies' night, there's a sports night, and there's specific nights like that. Now think about it, if maybe there was a low frequency night, so maybe there will be a, so the bouncer would technically be like the low pass filter, you know? It would allow for the lower frequencies to pass and not allow for the higher ones. Maybe if it was a higher frequency night, it will allow for the high pass to go in and not accept the lower frequencies and so on as well. For maybe for a band pass, it will want more for the middle ones, for the middle frequencies, and then for the band reject, it would not want the middle frequencies, it will want the super lower ones or the super higher ones as well. Here I have another example. This is of a high pass filter. So here we see frequency, the change in amplitude in dB. The F sub L or the lower cutoff will be 2400 hertz. And there's a 12 dB loss per octave. So here we have like 1200, we lose 12 D. At 600, we lose 24, 36. At 300, we lose 36, and so on. So question 3. What would be the F sub L and F sub U of a bandpass filter with a 800 uh, center frequency and a bandwidth of 250? So we have a bandwidth of 250. The bandwidth we usually have to divide by 2, which this means we have 125. And that 125 is what we subtract from 800. So 100 or also add. So for our lower frequency, 800 minus 125 will give us 675 hertz. And then for our upper one, we'll have 800 minus 125 equals 925 hertz. And now for question 4. So now if we want to find bandwidth, so what is it what we should do? So the question is, what is the bandwidth of a constant bandwidth filter with a low frequency cutoff of 2750 hertz and a center frequency of 300 hertz and an upper cutoff of 3250? So what we can do here is that we add the f of L and we subtract the f of u minus the f of L, So in this example, we have 302.50 minus 2750 equals, so 3250 minus 2750, that's 500. But remember, bandwidth is usually divided by 2. So in this case, we have to multiply it by 2, and we will get a bandwidth of 100. Okay, so it is also important to know that there are two types of bandpass filters, and pretty much the main distinct here is that if we have a percentage for a bandwidth, is that we have to multiply which is usually the center frequency to find the bandwidth. So in this case, if we have 60%, if the bandwidth is 200 hertz times 60%, it will be 1200 hertz. If it will be 8000 hertz times 50%, the bandwidth will be 400 hertz. So pretty much how does filtering also affect the original signal? So filter actually reduce energy at different frequencies. And pretty much we can also see this by the original and the end. So pretty much the input and then also trying to find the output. So pretty much trying to find how much energy is left at the output, or we can also find how much energy was originally at the input. So for example, if we're trying to find what was the energy at the output, we would put the input technically minus 10 log of a bandwidth, and then we're trying to find the input, we would use the output at the 10 log of bandwidth, and then we'll find it. So let's see with this example. So what is the spectrum level LPS of a white noise that has an overall level SPL of 100 dB and a bandwidth of 10,000 hertz? So here in this example, we're trying to find LPS. So we're trying to find the output. So we do 100. No, yes, we're trying to find the output. So 100 minus 10 log. So log of 10,000 is 4. So we have now 100 minus 10 times 4. 10 times 4 equals 40. So now we have 100 minus 40, which gives us an SPL of 60 dB. And this is 100 was our input and 60 dB is our output. Okay, and that's pretty much it for today. If you do have any questions, let me know. But apart from that, we're done.